Okay, today we will begin addressing the topic of hashing. Now, the things that we've looked at so far, manners in which we store data, are generally search-based. So it means that we have to go through the data by actually comparing various keys and deciding where to insert data. So for instance, with a linked list or with an array, sequential search comes into play. And that requires on average that we go through at least half of the items to be able to find the location of a particular item. In binary search, we begin with a sorted table of some sort, and then we're able to divide the table successively in two and ask whether our key belongs in the upper half of the table or in the lower half of the table. And so this works out to being a log n search algorithm. And a binary search tree is pretty much the same as binary search in an array. Binary search tree will allow us to restrict ourselves to only the left subtree based on the value of the node that's at the root, or the right subtree. And so as a result, we don't have to search through everything, but we either search to the left or to the right. Now, so the question remains whether there's another approach to storing and retrieving data that actually does not rely on searching through the data that is already in the container, table, array, linked list, etc. Hashing is that method. So with hashing, we can calculate the location of a particular piece of data directly. So if we know what is known as the key, and I'll talk about that a little bit more, we can apply a hash function to the key, and it can tell us exactly where that data is, and we no longer have to search through individual items. As such, then search for an item no longer depends on n. It is constant because the idea is that I can calculate the key. I can use the key and calculate the hash function in constant time, whether there are 1,000 items in the data structure or whether there are 100 million items in the data structure. With respect to every individual item, it's a constant cost for actually looking through the table. So the process of actually assigning a key to a location in the table is called hashing. And hashing is accomplished via what's known as a hash function. And I'll give you some examples of that in the next block. But right now, let's just take a look. The function must be able to convert the data type that's being stored. For instance, normally we will show examples of hashing using either string or integer data, but you may also need to hash a gas pump object, for instance, or a vehicle object. And so it's incumbent upon you then to come up with a hash function that is able to take that particular object and assign it a unique location. Now, while in theory, hashing gives us constant time access, order one access, in other words, this in practice does not happen all the time because of collisions. And I'll have more to say about collisions when we actually take a look at hash functions. So when do we want to use hashing? Well, anytime we're storing data, for instance, in a large database. Along with B trees, hashing is one of the primary methods that is used to store large databases on disk. We often hear terms like indexing and keys when we talk about databases, a lot of those come from hashing. And when should we use hashing? Well, it is best when we need exact matches in our data set. In other words, if I'm looking specifically for John Smith's record, then I'm able to apply the hash function and get right to that data. So anytime we're trying to answer a question like what data, if anything, is tied to this particular key, we're talking about hashing. On the other hand, what is hashing not good for? Well, we don't want to use hashing if we care about finding ranges of keys. For instance, we would not want to use hashing to store everyone's name alphabetically and then try to retrieve, say, all the people whose last names begin with A through F. That doesn't work very well, and as I explain hashing, hopefully that will make sense. We also, there's no such thing as a min or a max key, a minimum or a maximum key. So if we want to find, for instance, who's the person latest in the alphabet, we don't want to store the data in any type of hash table. And finally, if we want to process the data in some key order, that is not going to make a whole lot of sense with hashing either, because hashing actually redistributes the data throughout the table, as we will see. Now, it's important to not just think of this thing sort of in the abstract and ask ourselves, well, what's this hashing thing? And is it just part of the student harassment program? And I just have to learn to calculate this thing that has no use. Hashing is actually widely used. And here are a couple of C++ data structures that use hashing. So we'll look at sets, for instance. Sets are a way of storing different objects in a container, and the indexing for those objects is done through some attribute of the object and a hash function. And that's how we're able to store, for instance, Mary Jones in a particular set. There's some code, and I don't think it's that important to go through, but I think I think it just bears looking at the fact that we're inserting things like, for instance, the value 10 into a set. We're inserting the value 3 into a set. But what we're not given insight here is how this information is actually stored in the table. So once we say insert, the container takes over and calculates a hash function for using 10 first, and actually figures out where to place it in the table, and then it does the same thing for value 3, and we're able to keep these things in the container. But more importantly, we're able to recover these things later on. If I want to know whether 3 is in my set, we can go through and actually query the set and see if 3 is part of the set. There's a for loop there that shows you how to iterate through a set. Maps, on the other hand, are made up of key value pairs. And like sets, where there are multi-sets that allow you to have duplicates and ordered and unordered sets, maps come in those different flavors. There are multi-maps, which allow you to have duplicate keys, and they're both unordered and ordered maps. And the key here is that we instead of storing a single data item, we store a key value pair. And so you notice that the first code statement declares a map made up of a pair, where the first entity is of type string and the second is of type int. So in this case, the string is the key and the int is the value. So let's take a look at that next statement. We want to add something to map 1, and we want to use the key ABC and associate it with the value 100. This is how we would do it. This is akin to, for those of you that may be familiar with Python dictionaries. Python dictionaries are in essence maps because they store key value pairs. And so what happens when I say map, open bracket and quote, ABC, close quote, close bracket, the container takes over again and establishes a location for where it will store the value 100, and then it does so. And if we have a second item, we have item which is keyed by the string B and has a value 200. This can also reside in the table. And then later on, we can decide whether a particular value exists in our table. So the important thing that I wanted to bring up here is to just show you that these things are very much in use always. They're not just a theoretical subject. And while we don't often think about the guts and the gears of sets and maps, these in fact do work based on hashes, and that's how this information is stored in the various containers where the data is kept.